Hi everyone, welcome to Stats Rescue 911. My name is Lynn, and in this module I'm going to introduce you to the Chi Square Contingency test. We're not actually going to run the test, but I am going to give you the information you need to know in order to decide if this test is right for you. But before we go on, let me just point out that the symbol for the chi-square is a funny-looking X with the exponent of 2, and it is pronounced chi-square and not chi-square. All right. Now, some things that you really ought to know before proceeding with this module. You should know what inferential statistics are, what hypothesis testing is, and the meaning of significant. So if we say that something is statistically significant, what does that exactly mean? If you don't know what these terms refer to, then you can watch some of the other modules that I have posted or that I will soon post, and that will help get you ready for this module. All right. So the primary purpose of the chi-square contingency test is that it is used to see if two variables are related to each other. And before I go any further here, I should point out that the chi-square contingency test is also called the chi-square test of independence. And so you might see, depending on which article you read, which book you pick up, you might see contingency test or test of independence. They are the same thing. So let's look now at when you would do a chi-square contingency test. And the first thing is that you have two variables. Notice how the word two is all in caps because it is important. So you have two variables, and each of the two variables has at least two non-overlapping categories. By non-overlapping, we mean that a person or cat, dog, whatever you're looking at, can only fall into one category. They may not appear in more than one. All right. Typically, once you look at all the different category combinations, you will have 9 or fewer cells, and that's pretty typical. You have counted the number of people, and again, it doesn't have to be people, it could be things that fall into each category combination. And finally, you are testing the hypothesis that the two variables are related to each other. All right, so I think that this will make a lot more sense once we look at an example. Here, this represents some data that my students collected, where they went out and they surveyed other students and asked those students whether they love horror movies, like horror movies, or hate horror movies. And they made a note of which of those individuals were men and which were women. And this is the data that they obtained. So they found that among the men, 6 loved horror movies, 15 liked them, 7 hated them. Of the women, 13 loved them, 6 like them, and 11 hate them. Now, these are called observed frequencies because these are the frequencies that we observed by going out and actually collecting the data, right? So these represent the frequencies that we actually obtained through, empirical observation. These were observed. Now, that's in contrast to the expected frequencies. When we run this ANOVA, not an ANOVA, when we run this chi-square, the chi-square will calculate the percentage of people in each cell that we should expect to see if, in fact, the participant's sex has nothing at all to do with whether they love, like, or hate horror movies. All right, so again, these are the frequencies that we observed. All right, these are not calculated. These frequencies are calculated, therefore they are theoretical, and they are calculated in such a way that they will represent the frequencies of what we would expect to see if there's no relationship between sex and whether or not the participant loved, liked, or hated horror movies. All right? Okay, so let's assume that we go ahead and we ran our chi-square contingency test, and that test was not significant. If it's not significant, it means that the observed frequencies are the same as the expected frequencies. So in other words, what we found and what we expected to see are the same. Now, just use your logic here. If these frequencies, all the ones in these cells, represent no relationship between sex and movie preference, so no relationship, and if these are the same as these, then these up here must also represent no relationship. Okay? So, if your chi-square is not significant, this means your variables are not related. They are independent of each other. We can even say they are not contingent on each other. All right, but what if you ran the chi-square contingency test and it was significant? Well, you can't just say that the test was significant and move on. You have to tell people what the relationship looks like. And there are two ways of doing this. All right, so you are going to look at the percentage of people within one of the variables. In this case, I'm going to look at percent within sex. And then I'm going to show you what it would look like if you looked at the percent within the other variable, which would be percent within horror movie. Okay, but let's look at this one. So again, what you do is you look at the percentage of people within and then just one of your variables. So right now we're looking at sex. So if we're looking at percent within sex, then what we're looking at is the breakdown of the percentage of men in this case who love, like, and hate horror movies. All right, so we're looking within just the men. Okay, within means just within, just for a particular group. All right, and you know you're looking at the right percentages if they add up to 100%. So if we took this number plus this number plus this number, it would give us 100%. So what we can say is that for the men in the study, the majority liked horror movies. And then there were roughly the same percentage of men who hated and loved them. What about the women? Well, for the women, let's see, here a minority liked horror movies, 20% as opposed to the near 54% for the men. So a minority liked horror movies, and the majority either loved them or hated them. So that's the conclusion we're going to come to if we look at percent within sex. All right, and you would report it. That's the way you would describe it. All right, and that would tell people what's going on. But another way of doing this is looking at the percent within the other variable. So for example, percent within preference. So here, instead of going across, that would be percent within men and percent within women. If we want percent within preference, we need to go down. So we need to look at the percent within just a preference for horror movies, so love horror movies. And you know you're looking at the right percentages if when you add them up, they sum to 100%. So what we would say is among those individuals or within those individuals who love horror movies, the majority are women. And then we would move over here and then say among those individuals or within those individuals who like horror movies, the majority are men. And then finally we would say among those people who hate horror movies, in other words, among those people who are within the hate horror movie group, the majority are women. All right, so it appears that if we look within the people who love horror movies and hate horror movies, the majority are women. And among those who like horror movies, the majority are men. Now, typically, we would not explain the relationship by looking at this first table, describing it, and then going to this table and describing it. Usually, it makes more sense, or it's easier to describe the relationship with one table or the other. So you have to more or less look at both tables and then decide which of those makes the most sense. All right. And the goal is to describe the relationship as simply and as clearly as you can to the people who are inquiring about that relationship. Now, before we conclude, there's one more thing I need to talk to you about, and it's the Yates continuity correction for the perfect storm. Hope you know what the perfect storm refers to, but it basically means that everything lines up in a row, and if everything could go wrong, it does, and you get the perfect storm. So when would we have the perfect storm in a contingency test? Well, the first thing is you have a 2x2 contingency test. That means you have two categories of one variable, two categories of another, so you end up with 4 cells, 4 category combinations. The second thing is the chi-square test is significant. And the third thing is at least one of the expected frequencies is less than 5. Now, in order for you to have the perfect storm, all 3 of these things must be true. You must have a 2x2. The chi-square must be significant, and you must have at least one expected frequency less than 5. If all 3 things are true, then you have the perfect storm. And then you would consider, not necessarily use, but you would consider using Yates continuity correction. And what this correction does is typically it will correct for any inflated risk you might have of making a type 1 error. A type 1 error occurs when you claim that you have significant results. In other words, you assume that you really do have a relationship when in fact you have nothing. So it's a false positive. And when you have the perfect storm, there is a chance of an inflated risk of a false positive. So to correct for that, we use Yates. And Yates will make it a little bit more difficult, well, actually a lot more difficult, for you to say that your results are significant. There are people who believe that Yates continuity correction goes overboard, get it? And that it's too severe. And so they justify not using it, even if they do have the perfect storm. And certainly that's an option, but I just wanted to make you aware of this correction. All right, that's it. Those are the need to knows, and I hope this helped.